Hello, so we have seen product of two vectors, that is the scalar product and the vector product, that is the dot product and also known as the cross product. What we will be doing from here onwards, it is something that is called the product of three vectors. First we will be studying about the scalar triple product, and then we will be doing something that is called the vector product. Okay, so let us first see the scalar triple product. Because we are using the word triple, so naturally there should be three vectors. So let A, B and C be three vectors. The scalar triple product of A, B and C is the quantity we have to be very careful over here, because now we want to convert it into a scalar quantity. So over here I will write something like this: A dot B cross C. So this one, it is obvious that it will be a scalar quantity. Actually, if you have to calculate this one, which one will you calculate first? Will you calculate first A dot B, or will you calculate first B cross C? That is very important. Okay, so even though we don't usually write a bracket over here, but if we have to write it, this quantity inside, if we want to use parentheses or brackets, then we have to write it in this way. Okay, if we have to write it in this way, we have to write it like this. The brackets should be here. Why it should be here? It is because the cross product should be evaluated first. It should be evaluated first because the dot product is defined only for vectors. So over here, if you are taking the cross product over here, again you will be having a vector. So this one, it will be a vector times a vector dot a vector, which will give you a scalar. Whereas if by mistake you happen to write it like this, by mistake, then it is totally wrong. Okay, your mistake is really horrible, because over here if you are saying A dot B, it will be a scalar cross a vector. We don't have such kind of a multiplication, scalar cross a vector. We don't have anything like that. Okay, so you have to be very careful that if you see a quantity like this where there is a dot and where there is a cross, you will always have to evaluate the cross product first. Okay, so that is why it is clear that even if we don't use brackets, that we must calculate this quantity first. Okay, so now let us see one very important theorem. This one will be used, okay, if A equal A1i plus A2j plus A3k, B equal B1i plus B2j plus B3k, and if you are having C equal C1i plus C2j plus C3k, then A dot B cross C. Okay, it looks very complicated, but we can actually use this formula, which is just the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. So this formula, try to remember it. It is very important. We will encounter this. We will have to use this one in so many exercises. Okay, the proof for this one, I will leave it up to you. Okay, which is very simple. First, you just find B cross C, okay, and then take the dot product with A. B cross C, you can use the determinant and then take the dot product of A. You will reach this formula here. Okay, so that is all. What I will be doing now is this statement. Okay, the scalar triple product of A, B, and C gives the volume of the parallelepiped, Parallelepiped. So this one is pronounced as parallelepiped, gives the volume of the parallelepiped formed by the vectors A, B, and C. So let us first try to understand what is a parallelepiped. Okay, so if you remember, if you have to construct a cuboid, you will have to use the base as a rectangle. So if you have a rectangle, just stack them one on top of another, you will be having a cuboid. But if you want this object, what will you do? Okay, if you want this object, you will first have to have a parallelogram as a base. So let us take a parallelogram as a base. So this one is a parallelogram. Now what I will do, I will take okay, so just imagine this parallelogram is over here. Then take this parallelogram, take it upwards. Okay, I will draw it somewhere over here. Okay, somewhere, so something like this. Okay, and then I will join these four sides. This object, it will be a parallelepiped. Okay, it is not very clear. Okay, just let me draw it again. Okay, so what actually you are doing, you are taking a parallelogram. Okay, since the board is also tilted, it is not looking very clear. Okay, take a parallelogram on the ground, take another parallelogram above the ground. Okay, the same parallelogram, and then join the vertices just like you do. Okay, so this object that we are having, okay, it is a 3D object. This object, it is called a parallelepiped. So if what we are saying over here is that the volume of this object, it's equal to the scalar triple product. Okay, so I will do the proof for this. Formed by the three vectors. So if you have to form this object, you will need only three vectors. You will need this vector B over here, and then you will need this vector C, and you will need this vector A. Why do we need only these three vectors? Because as you can see, the opposite sides of parallelogram, they are all equal. C and C, A and A will be equal. Okay, similarly B and this one will be equal. So that is why we need only these three vectors to form a parallelepiped. What I will do, now I will find the volume of this object. Okay, just name this one. Okay, something like this. Okay, let's make it in 3D. X, Y, and Z direction. So now let us find the volume of this object. Volume of parallelepiped. It's equal to the volume of the parallelepiped. It is equal to area of base times, okay, area of the base into height. Okay, so the area of the base, over here the base, it is a parallelogram, right? So if you remember, we have done that the area of parallelogram, it can be written as B cross C, right? And the height it is this height over here. So this one is h times h. I won't be using dot or cross, otherwise it will be too complicated. It won't be clear, okay? Because I will be using cross only for the cross product, and I will be using dot only for the dot product. That is why over here it is just ordinary multiplication between this quantity and h. Okay, the reason for this one, again I repeat, it is because the base, it is a parallelogram formed by the vectors b and c. So that's why you will be having modulus or the magnitude of b cross c. Okay, so now let us see. This height, okay, just draw something like this, extend, it will be equal to this height. Okay, I hope you can imagine this situation in 3D. Okay, this height over here, it will be equal to this height over here. Okay, so now what we will do is B cross C. We will take a look at where the direction of this vector is. So B is pointing in this direction and C is pointing in this direction. They are in the XY plane. So if you take the cross product, you will have to curl your fingers like this, okay, in the plane, and it will point upwards. So that's why B cross C, it will point in this direction along Z. So B cross C will point along the Z direction, because B and C, they are in the XY plane. So if you take the cross product, it will point in that direction. This one, we can actually write it like this, HB cross C. It is the same thing because it is a scalar and the height is also a scalar. We can interchange them. Now just see, this is also h. Okay, this quantity, this length over here, it is still h. The angle between A and B cross C, let it be theta. Okay, let it be theta. So h, it can be written as A cos theta. H, it can be written as magnitude A cos theta, because we are having this triangle over here. We are having that triangle. We are having this triangle. So over here, this is the vector A. So this height h, it is equal to A cos theta. Okay, that is very simple, just by using trigonometry. B cross C. All of them are scalars. We can interchange their positions. B cross C cos theta. We can write it like this. Okay, and over here we have to mention what is theta, where theta is the angle between A and B cross C. Okay, theta is the angle between A and B cross C. So we are done actually. So this one, if you see, we can express it as A dot B cross C. Right? Because if you remember, x dot y, you can write it as magnitude x, magnitude y, cos theta. So instead of x, if you are having A, and instead of y, you are having B cross C, so this quantity will be equal to A dot B cross C. I hope that is clear. So always remember that the volume of a parallelepiped, it's equal to the scalar triple product of A, B and C. That is very important. In fact, I will write this one as a note right now. The scalar product, the scalar triple product of A, B and C, how will we denote it? It's denoted by A, B, C. Keep them inside a box and just write A, B and C without comma, without anything. Some of the books do use commas, some of them do use semicolons, but you can also you also do not need any symbol in between. So whenever you see this quantity box ABC, just know that this one is equal to A dot B cross C. Okay, so that is very important. So this one is the first node. The second node is, if you write ABC, you can also interchange it. Okay, you can interchange it because this one gives the volume. It gives the volume, so that is why we can interchange the positions. The volume remains the same, right? They are still the same vectors, so the volume of that object will still remain the same. That is why ABAC will be equal to BCA. It will be equal to CAB. Okay, so if you are maintaining this order ABC, 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 they will all be equal. Whereas if you interchange the order, if suppose instead of ABC you are writing it in the reverse order, then it will be negative. Okay, if the order is reverse, then if the order is reverse, then the value is negative. Okay, if the order is reversed, then the value will be negative. What I mean by this is CAB, okay, or sorry, CBA, you are reversing the order, it will be equal to minus ABC. Okay, CBA will be minus ABC. Similarly, if you are reversing the order, ACB, it will be equal to minus BCA. I hope that is clear. And similarly over here, if you are reversing the order, BAC, it will be minus BAC will be minus CAB. I hope that is clear. So always remember, if you are keeping it in the same order, then they will be equal, and if you reverse the order, then it will be negative. Again, this comes back to how the orientation of B cross C is. If you remember, when we were calculating the volume, B was in this direction and C was in this direction, right? So that's why B cross C will point upwards. Okay, whereas if you take B over here, if you are interchanging the order B and C over here, so it will point, the cross product of B and C will point downwards. That's why this negative sign comes into the picture. I hope that is clear. Also, the fourth node is again, which is the same thing. The dot and the cross can be interchanged. What I mean with this is A dot B cross C. You can easily write this one as A cross B dot C. It doesn't matter. Okay, but over here you have to calculate B cross C first, whereas over here you will have to calculate A cross B first. But they will both be equal if you interchange the dot and the cross. This works only for the scalar triple product. If you are having some other vectors, maybe 4 or 5 vectors, then you will have to be very careful when interchanging the dot and the cross. Okay, sometimes they may not be equal, but if you are having only 3 vectors and if you are having only the dot and the cross, then you can easily interchange them. Okay, number 5. Okay, maybe I will set this one as a question. If 2 or 3 vectors are the same, if 2 or more vectors are the same in the box product, then the box product is 0. What I mean to say by this is, that is, if you have something like this, maybe AAB, then because you are having two vectors of the same thing, that is A and A repeat, so you will be having it as 0. Similarly, if you have something like this, ABB or ACC, then you will be having 0. Similarly, if all three vectors are the same, okay, maybe AAA or CCC or BBB, then it will be equal to 0. So if two or more vectors are the same in the box, then the box product is 0. Okay, let us prove it. Proof: if two vectors are the same, then we can have something like this. Then AAB, you can write this one as A dot A cross B, but you must remember that we can easily interchange the dot and the cross, so we can write it as A cross A dot B, and because we have to calculate the cross product first, A cross A, it will be equal to 0, 0 bar. We have to be very careful to not just write 0, because it has to be a vector. So we will be having 0, 0 dot B will be 0. So I hope that is clear. Similarly, if you have something like this, ACA, if you calculate this one, it will be 0, okay, because two vectors are the same. Alright, so this is very important. So now what I will do is I will highlight a very important application of this box product. Of the scalar triple product. Okay, I forgot to mention the scalar triple product. It is also called as the box product. It is called as the box product because it gives the volume of that box. Scalar triple product or the box product. If you remember, the cross product, it gives us the area of the rectangle. Okay, the magnitude of the cross product, it gives us the area of the rectangle, and it can determine, just by using the cross product, we can determine whether the three points are collinear. This is kind of similar, but what I will say is this: the first application is it can determine when three vectors are coplanar. So the first application is this: coplanarity of three vectors. Coplanarity of three vectors. So three vectors are coplanar if three vectors A, B and C are coplanar if the box product is 0. Okay, what do you exactly mean by coplanar? Okay, it means they are contained in the same plane. For example, this vector, and this vector, it is coplanar. Okay, they are all coplanar because they all lie in the same plane, that is this plane of the board. Whereas if you are having a vector like this, okay, one vector like this, one vector like this, and I am having another vector that is pointing outside of the board, then those three vectors are no longer coplanar. So what I am saying over here is three vectors are coplanar if the box product is 0. As a proof, if ABC is 0, if ABC is 0, then the volume of parallelepiped is equal to 0. If the volume of the parallelepiped is equal to 0, so it means that we cannot form a box. We cannot form the parallelepiped with the 3 vectors. So that is why they must be coplanar. For example, just take a look at this. Okay, these 3 vectors, they cannot form a 3D object. They cannot form a 3D object because all of them, they are in the same plane. Whereas if we have a vector like this, and if you are having another vector that is pointing over here, then we can form a 3D object with these 3 vectors. Okay, so we cannot form, that is, the parallelepiped cannot be formed. From A, B, and C. Hence, they should be coplanar. Similarly, in the reverse, if they are coplanar, the parallelepiped cannot be formed. So the volume of the parallelepiped will be 0. That is why this box product will be equal to 0. That is all for now, but I will leave you with an exercise. Okay, determine whether the vectors A bar equal I plus j plus k, B bar equal minus I. Okay, I'm just making up vectors. And C bar minus 5i plus 2j minus 3k. Determine whether they are coplanar. Okay, so what you will do over here, I will just give a partial solution. You just find A dot B cross C. You just find the box product, which is A dot B cross C. Just find how much is it. If you remember, A dot B cross C, it is given by that formula A1, A2, A3, B1, B2, B3, C1, C2, C3. So over here will be 1, 1, 1, minus 1, 2, 3, minus 5, 2, minus 3. Just find this determinant, just see whether it's equal to 0 or not. If it is equal to 0, just conclude that they are coplanar. If it is not equal to 0, so conclude that it is coplanar. If it is unequal to 0, conclude that they are not coplanar. So it's a very simple exercise, just finish it. That is all for now.